Welcome back to the second video for lesson 4.3. I wanted to tie in actually concepts of 4.3 with some earlier concepts and using these contingency tables. So it says, suppose a study of speeding violations in drivers who use cell phones produce the following fictional data. So they either had a speeding violation in the last year or they did not have a speeding violation in the last year. And then the other question was, were they using a cell phone while driving or do they not use a cell phone while driving? And the total people that took the survey were 755. Find the probability that a driver is a cell phone user. So that is only answering the question of cell phone usage. So that means there were 305 out of the 755 who were cell phone users. And that comes out to be 0.404. Find the probability that the driver had no violation in the last year. So that would be only this category here. So 685 out of 755 is 0.907. Find the probability that the driver had no violation in the last year and was a cell phone user. So and means they have to be both. So it's kind of their intersection. No violation and a cell phone user. So it's where they crisscross, which is at 280. So 280 divided by 755 is 0.371. D says, find the probability that the driver is a cell phone user or had no violation. So the or is our addition property. But because being a cell phone user and having a violation are not mutually exclusive, they do overlap, is going to be this probability. So probability of cell phone plus the probability of no violation, subtracting the overlap. And the overlap is what we found here in this part C. This is the overlap. So we don't want to count them twice, so that's why we have to subtract the overlap. So the cell phone is 305 plus the no speeding of 685, subtracting the overlap of 280, all out of 755, comes out to be 710 out of 755 equals 0.94. This is the addition rule. E says, find the probability that the driver is a cell phone user, given driver had a violation in the last year. Given means we're talking about conditional. So probability that they are a cell phone user, given that they had a violation. So the cool thing is because we're using a table, we can just do this by using the table. So given that they had a violation means that only out of these 70 people are we talking. So given that we're out of these people that had a violation, what is the probability that that they use a cell phone? So that's 25 out of the 70. And that comes out to be 0.357. Then E says, find the probability that the driver had no violation given they were not a cell phone user. So probability of no violation given no cell phone. So given they had no cell phone usage, so out of the 450, no cell phone usage, what is the probability that they were not a violation? Pretty likely. They were much less likely to get a violation if they were not a cell phone user. So 405 out of 450 is 0.90, 90%. Example 8. The table below shows the number of athletes who stretched before exercising and how many injuries within the past year. So either they had an injury in the last year or they did not. And then we also ask the question if they stretch before exercising or they do not stretch. And there's a total of 800 people that were in the survey. What is the probability that the athlete stretches before exercising? So stretches before exercising is 350 out of 800 is 0.4375. What is the probability that the athlete stretches before exercising given no injury in the last year? Knowing out of the people that didn't have an injury, what is the likelihood that they exercise? That they stretch before exercising. I would think it's pretty high. That was the people with no injury. Who are the people that stretch? And that would be the 295. 295 out of the 514 is 0.574. The table below shows a random sample of 200 cyclists. And that's shown here, 200. And the routes they prefer. Let M be the males and H be the hilly path. So they took either a lake path, a hilly path, or a wooded path. And then we have just two genders, female and male. Out of the males, what is the probability that the cyclist prefers a hilly path? So out of the males mean that given the males. So what is the probability of hilly given that they're male? So out of the males, there's 90 males. Which of them prefer the hilly path? And that would be 52 out of 90. And that is 0.5778. And then it says, are the events being male and preferring the hilly path independent events? And that would be a no. Because if they were, then the probability of being male times the probability of taking the hilly path would equal male and hilly overlap. And we know the male and hilly is, if they're male and hilly, that's 52 out of the 200 or 0.26. And male times hilly, that would be male would be 90 out of 200 times 90 out of 200. Oops, out of 200. And so that would be 90 out of 200 be 0.2025, and those don't equal, so they're not independent. One last table. The table below relates the weights and heights of a group of individuals participating in an observational study. So we have height, tall, medium, and short, and then we have weight of obese, normal, and underweight. We have to find the total. So the total number of obese patients was 60. And then the total number of normal weight was 99, and the underweight, there were 46. And if we add those, we have 205. And then if we total the tall, we have 50. There were 104 medium height and 51 short. And if we add those, we also get 205. So there are 205 individuals participating altogether. Find the probability that a randomly chosen individual from this group is tall. So the probability of tall is simply all of the tall people, 50 out of 205, which is 0.2439. Find the probability that a randomly chosen individual from this group is obese and tall. The probability of obese and tall is where they cross. So obese and tall. So there's tall and obese. So it looks like this group of 18 right behind there. So that's 18 out of 205, which is 0.088. D says, find the probability that a randomly chosen individual from the group is tall given that the individual is obese. So the probability of being tall given that we know they're obese. Given that they were obese, there were 60 that were obese. So out of the obese, what is the probability of them being tall, which is 18 out of 60? And that comes out to be 30. Okay, what about the other way around? Find the probability that a randomly chosen individual from this group is obese, given that the individual is tall. So the probability of obese, given that they are tall. So out of the tall people, so out of the 50 that were tall, 18 of them were obese. So this comes out to be 0.36. Find the probability that a randomly chosen individual from this group is tall and underweight. So the probability of tall and underweight is tall and underweight is 12 individuals out of the total because it's not a contingent. So 12 out of 205 is 0.0585. And it says, are the events obese and tall independent? So if they're independent, then the and obese and tall would equal their product, multiplying their individual probabilities. So the and from above was 0.0878 or 0.88 divided by the product of these two is 0.714. And those do not equal, so they are not independent. And that concludes that problem there. And the last problem, example 11, kind of rounds up all of chapter 11. I'm sorry, chapter, I said example 11 rounds up chapter 4.3. The table describes the distribution of a random sample of 100 individuals, organized by gender and whether they are right-handed or left-handed. So what we didn't do is I didn't put a space for the totals, but it's good to have them. So there's 87 right-handed and 13 left-handed. Those add to 100. And there were 52 males and 48 females, and those also add to 100. So what is the probability of being male? That would be 52 out of 100, or 0.52. The probability of being female is 48 out of 100, or 0.48. The probability of being right-handed is 87 out of 100, or 0.87. The probability of being left-handed is 13 out of 100, or 0.13. The probability of being male and right-handed. So the and is the overlap. So male and right-handed is 43 out of 100. Probability of being female and left-handed. So female and left-handed is the least likely, 4 out of 100. Next up, probability of being male or female. Well, you're either male or you're female. So that would be 100 out of 100. Probably being male or right-handed. So because there's overlap, male and right-handed, then we have to use our addition rule. So probability of being male plus the probability of being right-handed, subtracting male and right-handed. So that would be 0.52 plus 0.87, subtracting 0.43. And that comes out to be 0.8941. Another addition is the probability of being female or left-handed. We have the probability of being female plus the probability of being left-handed, subtracting the probability of being female and left-handed. So 0.48 plus 0.13, subtracting 0.04. And it comes out to be 0.57. Okay. J, the probability of M prime, which is the complement of M. So we can find that by taking 1 minus the probability of M. So 1 minus 0.52 is 0.48. Okay, the probability of being right-handed given you're a male. So out of the males, out of the 52 males, the probability of being right-handed is 43. So 43 out of the 52 is 0.8269. The probability of being female given you're left-handed. So of the 11, or I'm sorry, of the 13 left-handers, 4 of them were female. So 4 out of the 13 is 0.8269. 3077. And last but not least, the probability of being left-handed given you're female. So we're going to do the opposite. So of the females, so out of the 48 females, 4 of them were left-handed. And that comes out to be 0.0833 repeater. And so that's kind of putting the first 3 sections of chapter 4 all together. With the multiplication property, contingent probabilities, and the addition rule. So catch me back for the last lesson of chapter 4, so 4.4.